Well, hello everyone. I'm Flanagan. I think we'll get started here. So I'm hearing a few echoes, and that's one of the first things I wanted to address from an administrative standpoint. We have live mics for everybody this morning or this afternoon, depending on where you are. So I request that you please mute yourself until you want to speak or until your presentation time is up. You can do so by just clicking on the little icon next to your name in the attendee list. Also, a couple other administrative things. We'll be recording the call today, and we'll make that available probably later on today. I'll send out a link to the recording once we're finished here, and we'll also make the slides available. With that, I guess we'll get started. And I'm happy to hand over the mic here to Sean, who will give a brief introduction and talk a little bit about some of the goals and motivations for the talk today. Sorry about that. Sean, are you there?
I'm here.
All right, I'll hand it over to you.
All right. Well, thanks, everybody. Thanks, Clay, for setting up and handling all the administrative aspects. It looks like we have 19 people online and 3 on the phone. I'm not sure if that's 19 total then or 22, but that's good. That's, you know, when we do these meetings, we generally have, you know, 60 to 100 people in community meetings, and it limits how much discussion can actually be done. I'm hoping with this group a little more discussion can be done. Am I in charge of the slides, Clay, or is that you? Did Clay leave already?
Sorry, Sean, I had muted myself. Yeah, go ahead. You can control the slides if you like.
Okay. How do I, well, I'm not sure how to do that.
All right, I'll control the slides then.
All right, next slide. All right. So before we really get started, I just wanted to let everybody know what the objective is so we can set expectations for the meeting. There's a lot of people online and a lot of information to share. The goal here is to share this information kind of very quickly and at a very high level in the hopes that, you know, we can form these collaborative relationships. ROS-Industrial is about open source, and open source more than anything else is not about free software, but more about collaboration and just not reinventing the wheel generally. We'd also like to introduce the developer groups in the Kuka community specifically. There are multiple efforts going on that I'm aware of, and I tried to bring those groups to this meeting. The goal is to consolidate that group into, you know, maybe 1 or 2 groups. So the goal is to consolidate that group. We also want to provide industry background on the current state of both the Kuka software, because I think there's exciting innovations there from Kuka itself, and on the ROS-Industrial side. So we've invited industry to this meeting as well, so that they can learn from this meeting and from the developers. And finally, I wanted industry to have an opportunity to share their wants and needs with the community. And if there's overlap, that's good to know, and that may even drive the community to develop certain capabilities, you know, specific to this Kuka platform, which I think is very unique. So here's the agenda. I'm going to talk for the first 10 minutes or so, but then I'm going to hand it over to Michael Gerstenberger from Kuka. I've seen him do many cool things with the LBR iiwa platform, and so I asked him to present. He was kind enough to do that. So he'll present for the first 25 minutes or so, and then after that we'll have developer lightning talks, which we'll try to hold to 10 minutes. and we have a good group of developers who are going to tell you, what they're doing, why they're doing it, and if they are open sourcing it, where that can be found. And then at the end, we'll have a little bit of open discussion, and I'm hoping that those from industry will see something and be able to share at a high level, their interest in a particular technology, or if they see something that's missing, let us know what that is. I know it's very difficult for industry to share that information sometimes, so if they can, I very much appreciate it. All right, so moving on to the introduction. Let's see, very quick introduction to ROS-Industrial. I'm sure most people on this meeting know a lot about ROS-Industrial, but in case you don't, the goal of ROS-Industrial is to take the advanced capabilities within the ROS software, which is an open source software for robotics in general, and just apply it to manufacturing problems and generate a community around ROS for industrial applications. As you can see from that little graphic over there on your right, robots pretty much, do welding, material handling, and dispensing of coating applications, and everything else is just kind of down in the noise. But everything else is really the growth opportunities that we see, and so we hope to enable those new applications through something like ROS-Industrial. And I put that a couple links down there. If you want more information, we got a web page that's it's more text than I'm sure anybody wants to read. But if you just like watching videos and cool demos, there's a link to our videos page, and I think there's a lot of good information there as well. So I'm gonna give the simple overview of the Kuka robot, which is, and Michael will do a better job of this, but I think we can all agree that the Kuka LBR is an exciting innovation in collaborative robotics, which is also kind of an interesting area to be working in as well. The idea is that, a platform like this can enable so many new applications. It's just very exciting. That's the reason we decided to hold this meeting is a lot of people from industry were coming to us saying, hey, we think there's a lot that this platform can do, but we'd like to learn more, and we'd like to know, if and how ROS-Industrial is involved in that. So it's kind of the motivation for all this meeting as well. But I'm not going to go too much into it because, quite frankly, I don't know all the details of the LBR platform as well as Michael does. So, but just so everybody knows, this is kind of the platform we're focusing on. So with that, I'm going to turn the discussion over to Michael, and I assume Clay is going to handle that for me.
Okay, am I live?
You're live, Michael. You should have control of the slides also.
Oh, how do I do that?
There should be little next and previous buttons. If not, I'll change the slides for you.
Okay, yeah, I'm not seeing next and previous.
Oops, hold on.
Oh.
Maybe now.
And I was just informed that I am now a presenter. Okay. Well, after the introduction, I need to have a brief apology because I'm not sure that everything that you were told that I'm going to talk about is what I'm going to talk about. What I prepared for today was a talk that basically describes a lot of the interfaces that are available on the Kuka lightweight robot. And so I was tailoring it to, how you might make use of some of those interfaces to fit into a ROS environment. And I guess I'd like to know right from the start, I prepared both for the LBR 4 Plus, which is the robot on the left, as well as for the new LBR iiwa. And if nobody's interested in the 4+, I can skip right to the iiwa part. So could we somehow choose which way I should go?
I think the priority would be on the iiwa, just given that that's kind of the platform that's going to move forward for industry use.
Yeah. Okay. All right. Well, maybe what I'll do is just flip through the slides and point out anything on the 4+ and point out anything that's particularly important. So, okay. All right. So I have this talk is structured first going through the 4+ and then the iiwa, a brief description of the controller platforms, then the programming languages and such, a list of the field buses that are supported on each platform, and then some of the Ethernet interfaces that are available on the 4+, but then the software interfaces that are available on the iiwa. So the 4+, if you have an predominantly orange robot, that's a 4+ or before. If it's mostly silver with orange caps, it's a new iiwa, and if it's a white one, it's medical, which is also probably an iiwa. This robot controller was based on our old KRC, based on that generation of controller hardware, the KRC2, and it basically made use of all of the infrastructure that was already available. One issue that came along was that doing things like impedance control, which is the main new feature that the LBR has, that was kind of a kludged-on add-on to how you normally did an industrial robot. As we'll see when we go through the iiwa, that software platform has been completely redesigned and now is much more integrated system. Okay, the 4+ was programmed in KRL, and it made use of system variables and data structures for accessing the special features of the LBR. There was limited expandability, although there was a package called the Robot Sensor Interface, which allowed you to do on the controller real-time sensor control. ROS-I is a little bit like LabVIEW that runs directly on the robot controller. Field buses that we supported on the 4+, DeviceNet was standard. You could get Profibus as optional, and if you wanted to do anything else, you needed to get your own bridge from one of those two networks. Ethernet interfaces, you could always access the Windows side of the controller from your network. So for things like file sharing and file transfers, that was available. We also had real-time software on the real-time side for communicating directly to your KRL program, and then also within the ROS-I framework, we had an Ethernet object that could stream data into and out of the controller. But most people, when they wanted to do any kind of streaming like that, ended up choosing the Fast Research Interface, which was designed specifically for the lightweight robot. Yeah, more on that coming up. So FRI was implemented. It uses Ethernet UDP packets, and it provides a hard real-time interface to the controller. It allows you to directly access the motion system. The update rate could be as fast as 1 millisecond. The slowest that we allowed was 100 milliseconds. And it had two different modes. Monitor mode allowed you to stream data out to a remote computer for logging or whatever purpose. And control mode actually allowed you to change the commands that were going to the robot, both either joint angles or Cartesian positions, as well as additional joint torques or additional Cartesian force torque vectors. You could also change the impedance parameters every tick. So, if you wanted to change impedance at a 1 millisecond update rate, that was possible. Some of the interesting things that were provided streaming out to the remote computer were position, of course, Cartesian as well as joint, command as well as actual, and then also forces and torques. But then also we provided the calculated Jacobian matrix and inertia matrix. As usual with a real-time or hard real-time system, good communication quality was essential, and we took steps to ensure that there was good quality of the communication channel. We also provided some C++ example code, although that was just an example. I would not recommend, it was written for Visual Studio, so I would not recommend that in a hard real-time environment. All right, so what's different on the LBR iiwa? Well, the controller itself is completely new. It's not even called a KRC anymore. It's called the Sunrise controller. It is based on the other controller hardware that we have for our other new robots, the KRC4. It's a little bit smaller than the KRC4 Compact, which runs our small Agilus line, and that's because the drives are not in the box anymore. The drives, are, like they are for the Agilus, the drives are actually inside the arm, so that makes the box a little bit smaller. As I mentioned earlier, the software is completely rewritten, and it's called our Sunrise.os. And the teach pendant for this system is the standard smart pad that we use on our other robots, but if you've had a chance to use it, you'll see that the HMI is completely redesigned as well. So how do you program it? This is another major change in how Kuka does robot programming. There is no programming on the robot controller anymore. All of your programming is done using a package that we call Sunrise Workbench, and that's installed on your computer. It's based on the Eclipse IDE, although there's some customizations there, so if you really want to use full functionality, you should run it on a Windows machine. We've had some people try running it on a Mac, and there's some limitations there. So you use the Sunrise Workbench to install the OS, to do any kind of configuration changes, for example, changing the IP address, changing which media flange you have, which robot you've got, field buses, safety system, as well as doing all of your application programming. The application programming is done in Java, and it uses the Kuka Robotics API, but the Kuka Robotics API is just the portion that makes the computer into a robot controller. If you still want to use other standard Java libraries out there, you're free to do so. In fact, we have one customer who has implemented a web server directly on the robot controller, and his customer is interfacing to the controller via a web browser. Multi-threading is supported. The only limit is whatever's practical. We don't make any restrictions on the multi-threading. So it's possible to have a monitoring thread in your application that's running sort of behind the scenes. We do also provide support for something called background tasks, and that's something where we actually manage the update rate. Where you actually, when you initialize the task, when you initialize the class, you tell it what the update rate is, that how often do you want to call the loop in the background task. And then another option that we have for the iiwa is called Sunrise.connectivity, and I'll go into more on that in a couple more slides. Field buses that are supported on the LBR are EtherCAT is standard. Profinet and ProfiSafe are optional, although if you're a North American customer, we're delivering those as our standard package. Basically, you have to ask for us not to have them if you want us to take them out. And then there's also field bus bridges that are possible. I know people have used EtherCAT to DeviceNet, or I believe also EtherCAT to Profibus. Whatever field bus you want to use, there should be a bridge for it. Software interfaces. I already mentioned that we can make use of standard Java libraries. Then there's the Sunrise Connectivity package, which has a couple of different components. The Smart Servo, and I should explain, connectivity is not intended to mean connectivity to the outside world, as in network connectivity. Connectivity really means access to the motion system. So what we have as part of that package is Smart Servo, which is basically a filtered access to the servo layer. In this case, we're expecting that the update rate is going to be on the order of 20 milliseconds or more. Basically, not right at the edge of even soft real time. One additional application area would be if your update rate is not reliable. So, maybe you've got a camera system that, nominally it's 20 milliseconds, but maybe sometimes it's 15 and sometimes it's 30. And so you want to do some filtering there. So Smart Servo would be a good choice there. Direct Servo, on the other hand, is intended for access at update rates, lower than 20 milliseconds, as fast as 2 milliseconds. And so that one allows you, and this is actually access from your Java program to the motion system. So, if you're able to calculate, the trajectory that you want the robot to move in at a 2 millisecond update rate, Direct Servo would be the interface you want to use. We also have a feature that, unfortunately, I don't have a lot of information about, but it's called Code Bridge, and it is supposed to be able to allow you to add your own C++ code directly to the controller. And some of the diagrams I've seen on it show both on the real-time side as well as on the Windows side. So, that's a pretty big change in robot controllers to be able to add your own code like that to our environment. Anyway, so that's another component of Sunrise connectivity. And the last thing I want to mention is that connectivity also includes support for the VREP package. Then, in addition to connectivity, we also have the replacement for the old Fast Research interface is now called Fast Robot interface. And that, okay, I think that's in 2 more slides. Well, I'll come back to the Ethernet. No, I'll do Ethernet right away. Oops, press previous. So Fast Robot interface uses the Ethernet interface to the controller, and I'll get into more detail on the Fast Robot interface itself. The Sunrise controller has multiple Ethernet interfaces, although really only one is intended for user use. There's one that's intended for your EtherCAT field bus, and then the main Ethernet interface is used for connection to your computer that's running the Sunrise Workbench. That same port can be used to access any of the Windows 7 networking features. So, for example, shared drives, we've done that. Both sharing a drive or sharing a directory on the controller so that other computers can access it, as well as having the controller attached to a shared network drive out there on your network. In addition to the Windows 7 networking features, you can also make use of any of the Java Ethernet communication classes. And so, if you want to do your own socket interface to a remote computer, that's perfectly fine, and you just make use of the standard Java libraries for doing that. And finally, the Fast Robot interface also makes use of that Ethernet interface. So again, Fast Robot interface is based on Ethernet UDP. It's a hard real-time interface to the controller. Supports direct access to the motion system, can go as fast as 1 millisecond. At this time, it supports, the monitoring supports joint positions and joint torques, both commanded and actual, and coming soon will be Cartesian force and torque. So that's on the monitoring side. The commanding side is now called FRI.motion overlay, and that is intended to be used at from 1 to 4 millisecond update rate. Currently, you can command joint angle adjustments, and again, coming soon, you'll be able to command Cartesian adjustments as well as additional torque, although that one is only intended for research customers. And then another component of FRI will be the C++ software development kit, which is basically like the example library that we provided for the old FRI. It's a development kit for your remote computer to access FRI on the controller. Okay, how are we doing on time, Sean? Looks like we got 10 more minutes. So shall we check out some of these application videos?
Yeah. We got 10 minutes. So there was one question though about CodeBridge down on the left from Christoph. He asked if CodeBridge was in the 1.51.
I believe so. Actually, I'm just bringing up 151 on my computer right now to see if it's in the option list. There is, in the option list, in the software option list for 151, there is a section called Tutorials for CodeBridge, so that makes me think that it's included there.
Hi, this is Phil Freeman from Boeing. Curious, we'll be getting our iiwa here next week, I think. I requested some of the documentation, and I got the Sunrise OS documentation. How do we get like the connectivity documentation and fast robot interface documentation? Should that be part of it, or will it be delivered with the robot? Do you know?
It should have been part of it.
Okay.
I'm checking the software, the disk image right now to see. One thing that's a little confusing sometimes is that we have a disk for Sunrise connectivity. That disk actually replaces the disk for Sunrise OS because connectivity is basically Sunrise OS with the connectivity built in.
Okay. Is connectivity an option, or is it part of the standard package?
Connectivity is an option, but as far as I know, everybody in North America has been getting connectivity. And yes, it's in the documentation structure on the disk.
Okay, thank you.
Hi, Michael. Thanks for checking on the CodeBridge. I've just installed it on my system, and the samples are empty, as well as for the haptic devices. Tutorials are also empty, so I actually don't know, and it's not in the documentation, so I don't know how to use it if it was in there.
Okay. Could you send me an email about that, and I'll have to check with Germany on that.
Okay, hey, Michael, this is Clay. I had a quick question also. Could you try to explain the maybe application uses of connectivity versus FRI? There seems to be some overlap in terms of the capabilities there.
Sure.
When do you use one versus the other?
Yeah. Connectivity is basically for use when, so why would you want to involve another computer if you've already got a quad-core processor inside the robot controller? Well, the reason would be if there were limitations on what you were allowed to do with the robot. But if you could write your own Java code, for example, that did your servoing algorithm directly on the robot controller at the update rate you're needing, then it seems to me that you would do that automatically. And so connectivity gives you that capability. It allows you to write your Java code and directly manipulate the motion system. It's only at the point where you have to involve a remote computer that you would really need to do something like FRI, which is basically an Ethernet interface that allows you to put a remote computer on the task. So, if you're wanting to do something with, say, Point Cloud Library, that involved a lot more computing horsepower than what you wanted to try to steal from everything else that's going on the robot controller, then that would be a good case for using FRI. So I would say if you need to involve a remote computer, FRI is a good choice. But if you can do everything that you want to do, if it's pretty compact directly on the controller, then connectivity alone would be a good choice.
Okay, thank you. Hey, one other comment on these videos. It's a little difficult to show the video over the web link here, but we can try.
Okay.
What happens when we show a video is the mics get muted while the video is playing, and then we come back.
Shoot, because I wanted to try to narrate.
Yeah, that's the problem. I don't know if the videos, do you think that'd be useful to try to show one and then talk about it afterwards?
Well,
or
if
should we
people
just
are going to have these links for later, I think that may be, that may be sufficient. And why don't I just go and describe the things that are being done here. Hose assembly is it's an application where I think it was actually like a dishwasher or something that had these flexible hoses, semi-rigid. They like to flop around a lot, and what we were trying to do was have the robot grab the hose and then insert it into the port. And the hose wasn't always where you expected it to be, but one base of it was always in a fixed location. And so what we were able to do was take the robot gripper, surround the hose, grab it loosely, and then slide along the hose until we reached, there was an end fitting that had a little bit larger diameter that basically allowed for a stop. And we could tell the robot to keep moving, out away from the body of the dishwasher until it felt something pushing back. And at that point it said, okay, stop, and now I know where that end connector is, and then it could take it around and then insert it into the appropriate port on the dishwasher. It did that for 2 different hoses, and then also had some kind of a solenoid that it was installing. Now, one of the things I guess I didn't mention, and because I was assuming everybody already knew this part of the LBR, is that the LBR has, in addition to the usual position control that a standard industrial robot will have, we also have other control modes for Cartesian impedance control, as well as being able to add a particular Cartesian force torque vector to whatever's going on in the process. So we're actually able to feel our way around the work cell just by using that intrinsic impedance control. All right, the next video is tending a friction weld machine. The robot in this case is using that force sensing capability to engage a door. It's a standard friction welding machine that's normally attended by a human operator, but in this case the robot's able to go up and open the door. At the point where it's first wheeled up to the machine, it actually makes use of the force sensing capability to go in and touch off the gripper on various key spots on the machine to calibrate, where it was located relative to the machine. Then it does the same thing for a depot of parts that it's going to insert into the machine, and then it starts grabbing parts from the depot, installing them into the machine, closing the door, and then the machine cycles and does its friction welding. So some of the nice things about that are that without any additional sensing, we were able to calibrate the robot to the work cell, and also so basically to accommodate uncertainty in where the machine is, where the robot is relative to those other components in the work cell. The kitchen assistant is kind of similar. In this case, it's being wheeled up to like a cafeteria tray return line. In this case, it's actually packaged trays that are intended to go out to hospital rooms, and the robot is taking the trays off of the conveyor and then installing them into a cart with different shelves. Again, it's imprecisely located, and so it makes use of that force sensing to calibrate itself relative to the cart, as well as calibrate itself relative to that conveyor. And then it's also one of the key things here is that it was also done without any fencing, and so we had the safety-rated torque sensing active, so that if somebody interacted with the robot unexpectedly, it would first pause, handling that first level of interaction at the application layer, and if you exceeded safety thresholds, then it would actually activate the safety-rated servos off. But normally you want to just handle everything at the application layer, and in that case, if you only exceeded that lower threshold, then you could resume the robot's motion by giving it a little pat, which we call a force gesture. If you pat it in the right direction, that's a command where it says, okay, he wants me to resume. The assembly of imprecisely positioned parts is again using that force sensing to basically figure out where these glass plates are relative to their fixture. They're just sort of tossed in there randomly. Well, not exactly randomly. They still have to fit. But they're not very precisely positioned in the depots, but they need to be very precisely positioned in the final assembly. And then the last one is the virtual wall with the surgeon assistant. This one allowed for hand guiding of the robot with what we call virtual walls, which were, in this case, it was in the shape of an inverted pyramid. And so the further you were away from the bone, in this case, it was simulating guiding a bone saw into a knee joint. And if you were up really high, then the virtual walls were very far apart, and so you could move the robot around quite a bit laterally. The closer in you got to the bone itself, the more tightly constrained the robot motion was. That one actually involved a separate computer because that involved a 3D camera system that was tracking markers that were attached to the bone as well as to the bone saw. So that's a summary of all the videos that you can take a look at on YouTube.
Okay.
Yeah, just one thing about the videos. I was following the videos while he was talking, and it was really fine. I just clicked in the links.
Okay. Well, Mike, I wanted to thank you for your presentation, and you know, one of the reasons that I'm glad that you were able to join us is that when we look at these robot platforms, at least from the research side, we kind of make the assumption that it's not going to have the power or capability to do the thing I want. But in talking to you about the Sunrise OS and the Java API, I think that's not entirely true. And so, like, those examples that you gave were very impressive. And as you said, for the most part, we're done using the standard Kuka tools, correct?
Yes. The only one of those demos that involved an extra component was the bone saw, and that needed the extra component for handling the camera. And that's something that's pretty important for me to emphasize, is that people who have experience with traditional industrial robots are used to the robots always being in position control mode, and whenever you want to do force control or anything, simulated impedance control, you're stuck with having to deal with the fact that, okay, force control is a layer that's on top of an underlying position controller, whereas with the impedance control modes that we have on the lightweight robot, that's completely different. It does not behave the same. And sometimes that leads to difficulties, but as long as you're in the mode where you understand that this is really true impedance control, then it's going to make things a lot easier for you.
Cool. All right. Moving on. Thank you, Michael, for your presentation.
My pleasure.
So now we're gonna let some of the ROS-Industrial developers talk, and these are going to be lightning talks. So I'm going to try and keep you to less than 10 minutes for these talks. And I'm very appreciative of all the people who submitted these slides, by the way. And we'll move on. This is going to be the first ones that are up. There's Fred Proctor, Jeremy Marvel, and Rick Candell.
Yeah, can you hear me? This is Fred.
Yep, we can hear you.
Okay, we'll start lightning fast here. We've got sort of two separate parts of the presentation. I'm going to lead it off with just a description of our overall research program here at NIST. The work's taking place in a program called the Robotic Systems for Smart Manufacturing Program, and Elena Messina, whom some of you know, is leading that up. The goal there is to look at NIST's sort of core mission area, which is measurement science, and we're looking at doing anything we can do involving things that fall into the measurement science category that enhance U.S. innovation and industrial competitiveness, and we're looking at various aspects of robotic systems, individual component performance, overall performance of the whole system, collaboration, agile tasking and retasking of robots, ease of integration of the robot systems components within the system to the factory, so that we can, and we're focusing on a assembly-centric manufacturing environment. So we're not doing medical, we're not doing process control. We're looking really at assembly applications. I've covered some of these projects here. We've broken the program into about 5 or 6 projects, and our outputs are typically things that you might see from as IEEE standards, ISO standards for safety, ANSI standards for robot performance, or Astm performance test methods. So the outputs we produce range from publications, but actually the sort of the final outcomes are standards that help make it easier to put robot systems together. I'm going to hand it over to Jeremy Marvel, who's now going to cover the work that we're doing in the collaborative robotics test bed with the Kuka robots. I guess, Sean, you have to unmute Jeremy.
I can see he's talking, but I'm not hearing anything.
Jeremy, do you have a volume knob on your end? Do I have to give up a presentation?
You shouldn't have to. Jeremy, do you have a mute on your end that might be on?
Maybe we can jump forward to the next slide, which would be, well, I appear to have control over the slide stuff here. I just nexted it to Rick Candel's discussion of the U-bots that we have. Rick, are you free to talk?
I am. Can everybody hear me?
Yeah.
All right, good. All right, so I had my phone and the web conferencing muted, so it looks like I turned it off right. Okay, so yeah, my name's Rick Candel. I work on the cybersecurity research project, and we are using the Kuka U-bot. We chose the U-bot because they are a low-cost platform for the kind of things, a robotics platform for the kind of things that we want to do. We weren't looking to do robotics research per se, but what we're interested in is purely how cybersecurity controls impact robot performance, especially the types of performance you'd want to see or measure in an assembly type scenario. So we're using ROS-Hydro. I know that we're not using ROS-Industrial at this time, but we're using ROS-Hydro, and I know that ROS has evolved since then. But the most stable software that we have for the U-bots happens to be linked to Hydro. We've implemented so far a basic collaborative testing framework, and I use the term collaborative kind of loosely. What we've done is implemented the ability to specify joint positions, commands, and various dependencies for the 2 robots within a YAML file or a series of YAML files. And so the robots are given their instructions through this YAML interface, and they know what the I guess the dependencies are as well. The dependencies meaning if one robot completes an action, it basically shouts it out, and the other robot can continue on, that kind of thing. So it's really more cooperative than collaborative, but that's the term we use. let's see. So as I said before, we're interested in cybersecurity research. So we're not looking for processing efficiency. Really, what we did was we put together a system with 3 computers and attempted to expose as much of an attack surface as possible. So we've got 2 controllers talking to a single driver computer, and joint positions and commands are all passed between those computers. So it makes for a good system by which we can do the kind of measurements that we want to do. But there are some limitations. As I said, the U-bots, we got 2 U-bots for less than 20,000 euros. So I guess that's relatively inexpensive as robots go. But what we've run into is that we're limited in the kind of tests that we can do. And the reason for that is that control is actually done within the robot. So currently, the driver code provided by the Kuka developers is very rudimentary, which is fine for a research-grade robot, but it kind of limits us at this point to just specify single-point trajectory commands to the controller, and then the controller says, okay, it basically uses a lookup table to determine what the velocities need to be, and that's basically it. It'd be nice to have an action server interface, as well as sometime in the future, if somebody would develop a velocity or torque controller, that would enable more types of research for us, more avenues for things we can do. And that's basically it. I just want to, the key takeaway for our project is that we're not really looking at specific robotic type metrics. We're looking at how cybersecurity impacts robot performance.
Okay, I'm going to jump. Go ahead.
Yeah, I was just going to say, if anybody wants to take a look at what we've done, there is a link down at the bottom of this slide. All the code is stored in GitHub in our U-bot repository, and if you get access to that, there's a video in there, an MP4 that you can take a look to see these robots in action. So it is pretty cool. So take a look.
Okay, Jeremy, are you on the line?
Yes, I am. Can you hear me now?
All right. Yeah. Thanks, Rick. Let me toggle back to the slide of our Kuka LWR 4 Plus and hand it over to Jeremy.
Cool. Sorry about that. I had switched over to a hands-free device on my computer because I was disturbing my wife who is studying for the GMAT. In contrast to what Rick just presented, we are actually looking at robot-specific technologies. As you can see here, we're actually using the Kuka LWR 4 Plus, which uses the KRC controller, and we do actually have the FRI option, but we are not actively using it right now. The key thing for us is that while we're doing some work with the LWR, we're not quite researchers, we're not quite developers, so we're kind of like the brunch of this particular group where it's not quite breakfast, not quite lunch, we're kind of halfway in between, where we're looking at producing platform agnostic kind of technologies. Some of these things include, for instance, inter-platform coordination and performance metrics and test methods. So we're, for instance, creating libraries such that we can have our LWR and our UR10 from Universal Robots using the exact same code base, performing tasks simultaneously together and actually exchanging information at a task-relevant level. We're also developing new test methods and metrics to assess robot dexterity. So this includes not only just the reachability, but also how well a robot can actually get around certain issues. And this is in terms of both grasping as well as manipulation with regards to the arm. We're also actively involved with developing safety standards for collaborative robots using the LWR, as well as mobile manipulator or robot arm on mobile platform kind of technologies. And are moving forward with ASTM, their new F45 group, for developing safety standards, test methods, and performance assessment standards for these mobile manipulators. And as Fred had mentioned earlier, we're really looking at industry or manufacturing relevant kinds of tasks. So going back to our inter-platform coordination performance metrics, we're also looking at multi-robot assembly strategies, test methods, and developing artifacts for those kinds of tasks. In terms of the future, what we have in mind for that, in the near future, we're going to actually start looking at HRI or human-robot interfaces for robot application diagnostics and prognostics. It's going to be using things like the Kuka LWR, where we can get some really great feedback from force or torques, as well as status of operations, where it is in the application, so on and so forth. And this is where we start diverting from the platform agnostic stuff, but we're also going to be looking at integrating the impedance control that we have with the Kuka LWR with impedance control that we're slowly but surely putting onto our shunt dexterous hand, outfitted with next-gen tactile sensors on the fingertips.
Okay, I think that's it. I'm going to fast forward a couple slides here to the who we are slide at the end. That's who we are. I'm the interoperability guy, and I'm looking at ROS and various other standards for different aspects of interoperability, like MT Connect, for example, if you're interested. And there's Jeremy, the LBR guy, and Rick, the UBOT guy. So thank you for your kind attention.
All right, guys. Thanks, Fred, and Jeremy, and Rick. We're gonna move quickly along here, but I would encourage anybody from industry and in the research side to reach out to the guys at NIST. They're very good at collaborating. All right, now on to Norwegian University of Science and Technology. Lars, one thing to say about Lars is his presentation can be focused more on dealing with traditional Kuka robots, but I included him because he's going through the fun process of submitting the ROS-Industrial. The reason it's important is to try and coalesce a group around ROS-Industrial or otherwise, but I really appreciate Lars for doing what he's doing.
Okay, thanks, Sean. Yeah, so can go to the next slide. Yeah, so I'm Lars Tingelstad. I'm from the Norwegian University of Science and Technology, Department of Production and Quality Engineering. And I'll start shortly about myself. I have a Master of Science in Mechanical Engineering, and I'm currently pursuing a PhD in Manufacturing Engineering / Robotics, which is hopefully finished by the end of this year. My project is on robotic assembly of aircraft engine components for the Boeing Dreamliner and the 747-8 jumbo jet. I guess that's the name. So I'm looking into assembling the turbine rear frame or turbine exhaust case, which is the yellow part on the image to the right there. And yeah, next there. Okay, so this is some recent images from our new Kuka lab at IPK. The top left image there is our what we call the Quantec lab, where we have 2 KR120 Quantec robots, 1 KR16 robot, and 1 KR5 ARC robot. And on the right there, we have our Agilus cell, where we have two Agilus robots, mainly used for educational purposes. And on the lower left there is a screenshot from a video made, I guess, half a year ago or a little bit more, of the first working prototype using move it for controlling the KR16 using ROS-I. And then next there. Yeah, so as I said, we have two Kuka KR120 RS2500 Pro Quantec robots, the KR16 and the KR5, and then the Agilus robots. And we use these robots for manufacturing purposes, typically assembly, welding automation in aerospace, automotive, subsea, and offshore industry, which is the main industries in Norway, as well as more traditional land-based industry like machine tending and those kind of tasks. And what's the main thing that I've been developing and trying to contribute to ROS-Industrial is Kuka ROS-I driver, which I hope many will see the need for, which is based on a ROS control hardware interface implementation, and then also support package, URDFs and support packages for the robots that we have, and also move it packages. And the support package for the KR120 is already merged into the Kuka experimental package on GitHub, and the ROS-I driver is currently being tested and developed, and are living in a pull request that you can see there in the link. And the goal is to get the ROS-I driver rigorously tested in our labs and merged into Kuka experimental before summer this year. And we're quite pleased with it. We're using it in multiple projects in our labs on a daily basis with not much trouble. So yeah, it's going in the right direction. Future plans for this software is also to get gazebo support for those robots. We're using it to some extent now for simulations. So yeah, that might be the next step. And then yeah, this is me, where you can contact me, and a web page where you can see some of my recent research results. Okay, thanks.
Okay. Thank you, Lars. And Lars, one of the reasons I invited you is I knew you were using the ROS-I interface, which can, I believe is something Kuka supports for factory deployable robots.
Yeah.
Michael, right. You might be able to chime in here, though. I don't. From your talk, it doesn't appear that this ROS-I interface is supported on either of the LWR or LBR robots. Is that true?
Well, we actually do have it on the 4 Plus. It's an option, but most people, on that robot, it was limited to a 12 millisecond update rate. That was the fastest you could go, and most of the customers wanted faster than that, and so that's what drove most people to FRI. But yeah, the ROS-I and force torque control that we also supply, which runs on top of ROS-I, is available for the wide range of all the Kuka industrial robots, the traditional ones. And we have a lot of really cool applications out there of people using that.
Cool.
One actually had an industrial application where they outfitted it with an ATI force torque sensor and a force dimension haptic interface, and they have an operator driving the robot around with a grinding wheel at the end, and he's able to feel when it's contacting the surface and the different features on the surface.
Oh wow.
Yeah.
Cool. All right. Thank you, Lars.
Yeah.
Now we move to Fraunhofer IPA. Pablo, or you up? Well, I can see you talking, but I can't hear you, Pablo. Yep, I still can't hear you. All right, Pablo. I'm going to skip past your slides, and then we'll go back. See if maybe you can reconnect and get the audio to work, or the phone option works pretty well. Okay. All right. All right. I'm going to butcher this, and I apologize. It's the Centro Piaggio.
Centro Piaggio.
I knew it was going to happen. My bad.
That's fine. I'm not Italian as well.
All right.
Okay, well, my name is Carlos. This is a package we started developing because, well, we were like searching about any open source implementations to control the Kuka Lightweight Robot 4 Plus, as you can see. And then it was really hard to set up a system to work, like, for instance, with oracles or stuff like that. So we thought that maybe with the new state-of-the-art ROS, Indigo, and Gazebo 4 stuff, maybe it was going to be easier to start developing from the current state of the art of software implementations. So we have been working on this. This is still a very experimental package. That must be said. That's why I don't have any formal videos of the real platform. I only have this. I mean, what you can see here is one of the main applications we're using is developing controllers. You see in the left, there is a video simulation of this is the RVs connected to the Gazebo simulation. So like it's the robot, the real robot is the Gazebo, but still the real packages are there to work with the real robot. And another main platform we are using is the bimanual robot that you can see in the right. It's all loaded into Gazebo with the PISA IIT soft hand already there, also implemented in the. There is also a hardware interface in simulation for the PISA IIT hand. So I'm gonna move here. So I'm sorry, I didn't have time to prepare well the slides, and so I follow the sketch that Sean sent. The main applications that we are addressing is grasping under uncertainty. You will find more info in the projects in the end about grasping under uncertainty, trajectory optimization, and planning in the loop control for compliant behavior. This is all work in the developed within the frameworks of research projects you will find in the end. What core of technology we are developing is about soft robotics and low-cost sensorization. Mainly, as you can see, we mount the PISA IIT soft hand in the end. It's a very adaptive hand, and low-cost sensorization refers to, since the soft hand doesn't have encoders, we have to manage to fit gloves, sensorized gloves in it. Development timelines. I refer to our issues and milestones in the GitHub that we are currently developing. I think this is the most important thing for me right now, the future development, because this is very experimental, so we would like to improve it more like in these three aspects. Right now, we would like to add stiffness trajectory control, in the sense that since we can control the stiffness at each tick, as said by Michael before, the thing is, I would like to treat the stiffness as a virtual joint with minimum and lower bounds, and just treat them like a position control, trajectory position control for the stiffness. Also, force position control for ROS-I, yeah, that Manuel, which is one of the person in the team, couldn't show up. He's working on this aspect. And also improving the simulation model, concerning the dynamic model. Right now, our gazebo model is based on the dynamics of cylinders attached like a chain. So one thing we can do, since this is also one call to Kuka enterprise, like we don't have the dynamic model, so maybe for research that would be another topic that you could release for research. So one thing is that researchers have done is to develop model identification. Actually, if you see, there are recent work about Alessandro De Luca in Rome regarding identifying the model of the Kuka. And another thing is to improve the hardware simulation interface. Right now, we are using the default hardware interface implemented in ROS control. But what we'd like to do is to improve it in the sense that we are right now using the joint stiffness control strategy as the default interface with the robot, since we think it's the more general. So the hardware simulation interface has to emulate, since the controller, the real controller, at the dynamics, mostly the gravity term in the control law. We would like to add this in sense that such that when you develop controllers for the arm and testing in simulation, it will behave as close as possible to the real robot. Is our software open source? Yes, of course, and you can find it here on the GitHub. It's already being used as well in another institutes. So I think this would be more useful right now. These are all linked images, so you can see this is the related research projects and funding, which this is based on. This is basically powered by ROS Control and Gazebo, ROS Indigo and Gazebo 4 mainly. So yeah, I apologize. I'm very tired. I didn't sleep last night. So sorry for the bad presentation I'm giving you. So if you have any questions,
can you hear me?
Yeah.
Okay, good. Thank you.
I want to say that we already implemented some external controllers from the basic controllers that are in ROS control. That's mainly the work of Manuel and Enrico. So you can test, like, you have like a very complex controllers like backstep and inverse dynamic controllers based on the poor dynamic model that we are using for now. This is cylinder based. So that's one of the issues that we have to solve in the future. Intentions or ideas porting this to the IIY. I don't know, maybe we have another group actually in the Roblox team. They are in another project, and they were given an II weight arm. But I don't think, I mean, it's not really, I don't think, I mean, I don't know the IIY, that Sunrise, that OS it works. Actually, that was one question I had for Michael, but I didn't forgot to do it. It was about how flexible is the code bridge to, for instance, to run ROS nodes inside.
Your line is now unmuted.
Can you hear me? If I can interrupt shortly.
Yeah.
I'm Servo from the TU München, Technical University of Munich in Germany. And to answer to Robert Krug, wrote in the chat, we actually have Marco Esposito in our team, which is close friend of this guy from Kuka. Yes, and he worked with them developing this interface that they show. Since he asked about the iiwa, I'm currently porting this to the iiwa, so it's more or less there, and I'm currently using I'm currently basing my work on their work, and it's quite easy. So it should be there in 1 week or so. It should be almost done. Just to answer the question. And yeah, and good job to the PISA guys, of course.
Thanks. Just want to say that for instance, in the B manual, I was expecting to have a very fresh video because we were submitting to the IROS conference, but unfortunately we had some technical problems not related to the ARM, and we couldn't finish the video. But we are actually moving the two arms using MoveIt as well, and with the two arms. So yeah, it basically works.
Well, Sean, should we try to go back to Pablo?
Hello? Yes.
Hi, Pablo.
So thank you for inviting me to this meeting. So I'm the new here, and well, I'm from Fraunhofer Institute in Germany, and I've been working with the iiwa for 1 year more or less. First with a prototype, and now with the new iiwa. And well, we can go to the next slide, or do I have to control? Yes. So this is our pilot case we have already developed. It's a human-machine collaboration in a riveting operation. So we integrate different components, software and hardware components, and exactly what we do is localization with a Kinect camera. Then the robot moves according to the position of the part. With two cameras, two stereo cameras, we do a fine localization from the hole, and then we perform a riveting operation. So this is everything integrated in a framework, and the idea is that a normal worker can easily and fast program this system. So with different robots, different components, and the integration will be fast and cheap. So we can go to the next slide. What I already developed is in the iiwa part, a Java application which does an interface for a ROS node. And well, we have this command line interpreter. We send easy commands, and we return the answer from this Java program. So it's like a normal TCP socket. And well, as already Michael commented, the iiwa has different controlling modes. Well, I'm already used it the 4 different control modes, the normal control mode, but we had a problem. The frequency is very low and we cannot use for reactive operations. Then already we integrate the impedance controlling in the whole process, and we use the smart and the direct mode to control, so to do, for example, a PID controlling. So right now it's in C++, the ROS node program, and we have different interfaces, different topics, and we can also controlling with a self-defined ROS action everything. So it's like a big application. It's not so big. It's about 1,000 lines, but slowly it has grew, and now it's not so easy to manage well. And the operation we can do is the following. So we can publish already in ROS joints, frames, force and torque in Cartesian and in joints using the standards. And also we define our self-action to point-to-point and linear controlling using Cartesian and joints coordinates, so joints configurations. Also, we already integrated with MoveIt and with the ROS-Industrial standard, but here we have a problem, which is the trajectory. This trajectory definition is too mathematical for us, so we need to send vectors, small vectors with a target position or an increment, and the speed to arrive to this position. So we discover a small problem, which is we can only give the speed in the Kuka with a percent. And well, we need to discover another way to do it. And well, our feature plans is to divide this big application is small nodes. So this is already started, and the basic MoveIt ROS essential driver and the communication node is already done. Well, continue our pilot case, and we want to publish an open source version in a few months or weeks. So this is the idea. And well, so my contact is my contact data. So well, if you have any questions or something you wanted to go deep in, so I'm welcome. So.
Thank you, Pablo. Sean, are you still with us?
Yeah.
Okay.
I am now.
Okay.
Hi, Dan. Yeah, thanks, Pablo. I was going to say we're going to move along to Risto, so we stay on track. Risto, you ready?
Hi, can you hear me? Good. Hello?
Yeah, we can hear you, Risto. Go ahead.
Okay, good. Hi, everybody. My name is Risto Kuichev, and I'm a second-year PhD student at the Italian Institute of Technology and the Biorobotics Institute at Scuola Superiore Sant'Anna. And my main focus of research is medical applications, especially using robots for different surgical interventions. What I'm currently kind of work on, depending on my time, is exactly this application, where basically the goal is to use flexible interventional tools. Here in the picture A, in this example, you can see we decided to use a flexible needle where is guided based on an ultrasound images. So this has a great medical applications, especially for tumor ablations, bronchotherapy, etc., where basically the ultrasound is picked due to its non-ionizing radiation and its small footprint, so it can be very easily integrated into a robotic system. And what I plan to do during my PhD thesis is to use basically collaboration of two robots, one which is the Kuka lightweight robot 4, and the other is the one robot we built recently. It's a 2 degree of freedom robot with a rotational and linear axis, which are meant to guide the needle into the human tissue. So the first problem I had to solve was the calibration of these ultrasound images, So it was basically finding how the ultrasound images correspond to the optical tracking frame, which is basically a new tracking frame we developed, which is a multi-phase and can increase the workspace of the robot. Basically, you can do a 90-degree rotation and still be tracked by the optical tracking system. So this is seen in the picture B, basically in how the ultrasound calibration is performed. It's the ultrasound attached to the robot, and we have N calibration phantom. For this, we used an open source software which is called Plus, and it's basically developed by the Queen's University, the PERC lab in Ontario, Canada, and it enables us to basically use this robot in order to calibrate these ultrasound images. So basically, here are some examples of what we are currently doing with the Kuka. Is just for now using it for calibration and doing mainly a 3D volume compounding based on the ultrasound images. So on the left side pictures is the developed hardware we have, and on the picture D is some of the results we could achieve. And basically by using this Kuka robot, we have a better volume compounding compared to the freehand calibration because we are able to control the movement and to during the calibration, which is essential to minimize the error. So for example, to get during freehand calibration, we could have get 0.6 millimeter reprojection error, while by using a robot, we get a 0.4 millimeter reprojection error, which is, I think, very good compared to our application, because we have to precisely locate where are the target for the flexible instrument to reach on. So this is very shortly my presentation because it's in a very early stage of development. So more will become. We haven't used any. I'm still in kind of thinking to use ROS or not. I already tried the Centro Piaggio guys package for the Kuka lightweight robot a month ago or so, and seemed to be worked, but I haven't tested it thoroughly. So, and I am still in the thinking whether ROS can be used for my application or not. So it has a great potential, but I still have to look a little bit more to this towards this. So very short. Thank you for your attention, and here is my contact information. If you have any questions, please contact me. Thank you.
All right. Thanks, Risto. I think medical applications are really cool, and the Kuka robot is particularly, the capabilities are going to be very useful for that. So I'd like to encourage all the developers to cooperate as much as they can. There are multiple efforts going on, and if we can all collaborate, that'll be good for everybody. But at this point, I'd like to open it up to questions or general discussion from the audience. People from industry, if you have any particular questions, that would be great as well. Well,
maybe your line is now unmuted.
One question. This is mainly for Michael from Kuka directly, because as far as I saw, everybody that is involved in using the iiwa so far is not actually using the FRI connectivity option, me included. That's the feeling that I have is that current is too limited in the sense that only adjustment to the motion it's allowed, and not completely full motions. The messages are allowed to the stream. Is it correct, or am I or other people looking at the wrong thing, maybe on the wrong angle?
I think that's correct. Oh, getting an echo here.
Okay, so
I did notice that there are a couple of key features that I expected to be there that are slated for the next release. Yeah, I think at this point you can only adjust joint angles.
Michael, is it that you can only adjust a path as it's executing, or can you send joint angles as kind of like waypoints?
Well, we have a special instruction called the position hold, which is basically it's an open-ended motion. It activates the motion system and allows for adjustments to be all relative to that point, and it never terminates. So, it's effectively you can do either way.
Okay.
Okay. I have a quick follow-up to what Michael just said. So we are actually using or try to use this position hold to stream a joint trajectory from ROS, but this doesn't allow to affect the parameters like jerk or velocity of the underlying controller. We get, depending on which trajectory we try to follow, a pretty bad behavior of some joints of the robot. Is there anything we can do about that or adjust this in some way in the current state?
Well, that's where I like to say, with great power comes great responsibility. If you're wanting to stream the data at a high update rate, you really need to make sure that stream is at least, generally C2 continuous. So if you want jerk limited, you have to make sure that the path itself is jerk limited. If you're talking about, some of the effects of running through the inverse kinematics, that as you get closer and closer to a singularity, the accelerations and jerks really skyrocket. Yeah, there's not a lot you can do about that. I guess if it's entirely sensor controlled, then there's really not much you can do about it. But if it's sort of pre-planned, you could run it through your own inverse kinematic model.
I'm just talking about the joint targets, not end effector targets. So even if we just stream sine motions, let's say, to test trajectory following simply on a joint level, even there we get bad behaviors, although those trajectories are definitely consistent and derivable.
And so you're saying it's not doing what you asked it to do?
It's doing what we ask it to do, but for some joints we get sort of vibrations, and I think it's due to the underlying control scheme, which tracks them well, but this results in sort of vibrations at some joints.
Okay, so maybe it's hitting a resonance?
Maybe, I don't know, but even if we just stream a slow sine wave position control, which we try to track, it's very hard to do this with this position hold control mode in our experience. And if you use, for example, instead the smart or direct servo, there you can adjust the acceleration and jerk characteristics of the underlying controller, which you cannot if you actually use this position hold, in our opinion.
Okay, I'm not aware of that.
Oh, okay.
Quick question for Michael.
Go ahead.
I just was curious about not providing the dynamic model of the Kuka arm. So, do you think it would be possible to open that to researchers?
We keep asking, and that's something that's decided in Germany. So
right.
I I would not hold out a lot of hope for that. Sorry.
All right. That's fine.
Okay, guys, it's 10:30. I think we can. If people want to stay on and talk, we'll stay a little bit longer. But I wanted to thank all the speakers and thank all the participants for your time. And we hope this was useful. We'd love to get feedback. So feel free to send. That's me, but feel free to send this guy right here an email. No, and you can send either one of us an email and let us know what you thought. Yeah, we'll keep this up a little bit longer if the discussion continues. But I just wanted to let everybody know we reached time. All right, did I just kill the conversation then?
Well, if I could ask one question. This is Gijs.
Go ahead.
Yeah, so I noticed that...
Who's talking now?
Do we need some arbitration?
So I have a question to Pablo. I didn't know if he said it, but I wanted to know if the ROS implementation is based on ROS Java or on the C++ code bridge thing.
No, it's an independent application. So the Java application is a normal Java application in the Sunrise controller. And I open a normal Java TCP port, and the communication is streamed line by line. So I sent a line with the command. The command is processed in the controller, and well, I call the corresponding Java function or the direct servo motion and smart motion, and I give immediately an answer back. And well, so they are completely independent. So it's a small Java application, very small, and the only thing I do is read the commands and call Java functions.
All right. Have you tried with ROS Java and seen maybe any advantages or disadvantages to implementing the communication yourself as you did?
Well, yes, I already tried, but the problem was the difficulty because, well, this basic application I did more or less in 1 day, so I was working in 1 day, and with ROS Java I was trying during a week, more or less, and I didn't achieve any success, and then I give up to continue because, so this was, I needed really fast to be done, and yes, and I didn't went into the ROS Java details. So
based on a implementation by some guys from Stanford University, we are currently using a ROS Java implementation that is working, but it is by far not as large as your presentation. So I'm very interested in seeing your code then.
Well, you can email me or can we speak later, I think.
Okay. Heish, go ahead. You had a question?
Yeah. So I noticed that many of the people developing drivers for the Kuka arms were exposing some kind of Cartesian control mode. And I was wondering how they went about that, because obviously there's no, well, as far as I know, there's no standardized way in ROS to communicate Cartesian trajectories. Neither is there in ROS-Industrial. So perhaps some of the people developing these drivers could tell a bit about how they did that and whether we should pursue a standardized Cartesian trajectory message.
So
I would like to mention here, guys, Gish, are you using the ROS control framework? I remember, right?
I think so. Yes, more or less, but not exactly. So we develop our Astm, so Astm message, and we use it for advanced controlling of the Kuka.
All right.
But the Cartesian message is not a standard ROS message. Was it a special message that you developed? How about you, Pablo?
Hello? Yes. So what was the question? I didn't hear it.
So in handling Cartesian motion, there's neither a ROS message or a ROS-Industrial simple message that describes Cartesian motion. Did you have to create your own?
Well, in ROS there is one standard for position with pose and quaternion, and we use them in one array like a trajectory, but there is, I think, no standard definition for a Cartesian trajectory, and we implemented our self message. So it's an action, so action seen like services, but with feedback, and we use them for controlling all this operation. And then after, I started to develop the ROS standards, so the standard movie interface and topics.
Okay.
Then there's a custom message to send all the data. Also, you can send stiffness to update the impedance control mode if you want to do that. But yes. It's not standardized at all. So maybe like what Pablo was just saying, it would make sense to find some common ground here to standardize that.
Well, yes, that's true. We need to send the impedance values, and also, for example, for force movement, force in the 3 Cartesian coordinates, and time. So it's important because, for example, an impedance operation can be finished by time or by position. For example, I try to arrive one position, but there is an object in the middle. Then the robot collides with this object. So the position is never arrived. And then I need to stop this movement after a few seconds. So, yeah, this pilot case, we use it like this. So we detect if a hole was correctly riveted, if was inside the hole. So it's maybe difficult to clear it, but well, so we need very variable things. So
okay. It's definitely not a simple kind of message, or maybe it's multiple messages. It's sounding like for impedance control versus Cartesian control. But it's I think it's something unique to this community because you have this capability in your robot, and more traditional robots don't necessarily have it. So hopefully this community can come together and, even if it's in an ad hoc way through, just releasing open source code, come to a common message that would be great.
Yeah. And if it can be fit within the ROS control framework will be okay, because then everyone can benefit, not even for the Kuka arm, but for any kinematic chain.
Sean, this is Phil Freeman. Do you think it makes sense to create something like a working group within the ROS-Industrial consortium to try and figure out what are the messages that would be required for something like the iiwa? Because it does sound like there's a need to create some new simple message formats or some new message formats for the iiwa that don't exist for the other arms that are currently part of the package.
Yeah, I definitely agree. I think it would be I agree. I can kind of take an action item to get something like that started. Because this is a very unique arm, although we hope in the future a lot of arms will have this capability, it's probably a good time to try and put something like that together. Thanks, Phil. Any other discussion? Nope. Okay. Well, it feels like we've reached kind of the end of the discussion. You know, all the contact information is out there, and the meeting will be recorded, so we will send out a link. I'm hoping that, you know, the various groups can get together and hopefully this spawns some collaboration. But thank you all for your time.
Thank you.
Bye, everyone.
Bye.
Bye-bye.
Bye.